only briefly. Our first speaker is Carolyn Oldham. She is a Winthrop professor in the School of Environmental System Engineering from the University of Western Australia. So Carolyn has worked on many disciplines. He especially experts in the cross-disciplinary approach in transport process, environmental engineering, environmental chemistry, and also spatial and temporal patchiness problems. In addition to being an excellent scientist, she is also a very excellent teacher, so she received National Australia Learning and Teaching Council Award for her outstanding education. Today, her presentation title is Scale and Balance. Let's welcome Carolyn.
Okay. First of all, thank you very much for the invitation to come and talk to you today. That's okay. As has just been said, first of all, I'll give you a little bit of background, which the cross-disciplinary nature of where I've come from is quite important for what I'm going to say today. So my first degree was in pure chemistry, and then I moved into environmental engineering, and specifically limnology and turbulence in lakes. Since then, I've become more and more interested in material fate and transport, and that is material, whether it's defined as nutrients, contaminants, or biota. And so this talk is really about how do we describe or classify systems based on material fate and transport. And I've worked in limnology, in oceanography, in estuarine science, more recently, over the last 10 years, more and more with catchment scientists and biologists. And what I'm doing today will bring in concepts from all of those fields, and as we go through, I'll be doing some translation of some of the different terms from one field to the next. So the outline of the talk is, first of all, go through some context, some of the problems that we've been working on over the last 20 years, then go through some of the classification approaches that is the main body of the talk. I'll give a short case study of an acidic wetland and how we use this classification system, and then I'll just start to touch on some of the ecological consequences. And I think it's the ecological consequences, or how you apply this framework to the ecological functioning, that I think is the most exciting part. But I'll just touch on that at the end and leave you with some questions. So first of all, the type of examples or the context that we've been working on. This is from a study about 10 years ago where we were trying to understand the nitrogen that was applied to these agricultural fields, how it was transported down into the riparian zone. This is a very degraded riparian zone. They've just fenced it off to prevent the sheep from coming into the stream. In this system, the groundwater is very close to the surface water, and so a lot of the transport pathways are subsurface pathways. And so we're trying to understand, as the nitrogen moved from the fields into the stream, how often did it move across the surface, and how often did it move in the subsurface. And more particularly, the question really was, how large should this riparian buffer zone be to ensure that it did its function, it did its work, and at least retained or took up or removed some of the nitrogen, if not all of the nitrogen. Another context that we've been doing, this is in Western Australia. This is a hypersaline, hyperacidic lake over near the goldfields in a very arid part. It is naturally so. The pH is around 2, and it's hypersaline. And one of the questions becomes, this acidic water is recharging, these lakes are recharging the groundwater. So what is the extent to which this acidic water is carried into an anoxic subsurface system? So another area we've been working in is around canopies and emergent vegetation, and the question there becomes, what is the material transport through the canopy, and how does that vary with flow through the canopy and also density of the canopy? So as we're moving through these contexts, we're working across a number of different scales, from the larger scale of a catchment through to quite a small scale at the canopy, in the canopy context. A lot of other people have been looking at the effect of transport on some of the ecology, and this is some really nice work published just last year, and looking at the effect of flow, but now on species richness, and this is in a subtidal inlets in Palau and Alaska, and showing that as the flow velocities in these inlets increase, the species richness also increases. So there's obviously some connection here between the transport and the physics and the biology. There's also been work done at a much smaller scale again by Boudreau and Jorgensen and their group. And that work has been focused, among many other things, but looking at the effect of flow on the transport of solutes from the sediments when you have a rippled surface. So here is a flume that has a flow moving, unidirectional flow moving across it. There are ripples in the sand, and once the flow is started, then you start to get a drawing up of the solutes from the sediments. So all of these contexts, all of these questions that have been raised that people have been working on for many, many years have all been looking at the fate and transport of material across all different scales. And so if we're looking at that, if we're interested in that, we can't do anything without really using the advection diffusion reaction equation if we're trying to quantify these processes. So this is the advection diffusion reaction equation. So here we have just briefly an equation for the change in concentration of B with time, which is a function of an advective term where U is a mean flow, a mean velocity, times a gradient in concentration. There is also the diffusion term where we have the effective diffusion coefficient here. So both of those are the transport terms, and then we have a reaction term. So I will use this equation again and again and keep coming back to it as we try to use it to help us classify a number of different systems across a number of different scales. So first of all, I look at dealing with transport. So there are two, as we said in the previous slide, there are two fundamental forms of transport, if you like, advection and diffusion. And in both of these, we have a really key concept, and that is what's been known as the residence time of a system. If we have a control volume here, this is an emergent canopy. In this system with an advective flow, the canopy is quite sparse, and so you do get a good mean flow through the canopy. And so we say that at time zero, the initial time, the flow enters our control volume, and at the final time it exits the control volume. And that time difference has been known as the transport time scale or the residence time. That concept is the same whether it's diffusive flow. So this is a much denser canopy which doesn't allow a mean advective flow through it, but we have the same concept that there is a transport scale, a time scale. It's much longer than an advective transport time scale, but there's still the time it takes for a particle, whether it's biological or not, to move from here to here. I'm going to change the language here because ultimately I'm interested in the fate and transport of material. I'm not interested in transport for the sake of transport. So I'm going to change the language here. Rather than saying the transport timescale, I'm going to talk about exposure timescale. So this is the time some material has the opportunity to react, whether that's a biological growth or chemical reaction or particle settling. So it's the time it takes, the opportunity timescale or the exposure timescale. So it's a change in the language, but it's a very important change in the language because it immediately shifts our focus to material behaviour. So that was transport, just setting up some initial concepts around transport. In reaction, we have very simple reaction, a chemical or material A plus B going to C and D. We have a rate constant. Now that rate constant has been parameterized or described in many different ways. If you're just interested in the chemistry, we use simple first or second order kinetic equations where the change in B, change in concentration in B, is equal to the rate constant times A times B. If A is in excess, we can make a pseudo first order reaction. It's where we have a pseudo first order rate constant, and then we can get a time scale for the reaction. And that time scale for the reaction is simply the reciprocal of that rate constant. Similarly, if you're interested in the biology, you have a much more complicated equation using a monod kinetics, an equation for describing how B changes in concentration with time, and it involves specific growth rates, and you have the monod equation, but you can still extract a characteristic time scale, which is a function of the maximum concentration you experience and the maximum specific growth rate. So whether you deal with monod or biological kinetic descriptions or chemical kinetic descriptions, in both strands you can get a characteristic reaction timescale. So my proposition is that when we are classifying systems, what is most useful is actually the ratio of the exposure timescales to the reaction timescales. And what that does is forces us to go through the process of quantifying the exposure timescale and quantifying the reaction timescale. And this ratio of two numbers, the two timescales, I'm going to give a label, NE, and it's a non-dimensional number. Non-dimensional numbers have been used a lot, particularly in limnology and oceanography, but in many other areas, to classify systems. Non-dimensional numbers are particularly used a lot in engineering, and one of the non-dimensional numbers we're all most familiar with is probably the Reynolds number, which classifies a system according to whether it's turbulent flow or whether it's laminar flow. There's another non-dimensional number that catchment scientists use all the time, which is simply the hydraulic gradient. And what that gives us is an immediate conceptual model in our mind, as well as for numerical purposes, of whether we're going to get strong flow groundwater flows or much weaker groundwater flows. So we are using non-dimensional numbers all the time. They're simply ratios. And I guess coming from engineering, I'm always looking for non-dimensional numbers which will help me to classify systems. So going back to the advection diffusion reaction equation, we're going to say that there is a first regime where advection really dominates, and I'm going to say that the diffusion, for all intents and purposes, can be neglected, and I will call this regime 1. The types of systems that are in regime 1 are flow-through wetlands, which are experiencing a high hydraulic head on either side, and you get flow moving through, advective flow moving through the systems. Also an emergent canopy where you have sparse canopy. In porous media flow, where again you have a large hydraulic gradient, you can get advective flows. And also the context of a strong river, a high-flowing river coming out, and the outflow plume moving past a series of reefs or islands. So all of these are examples of regime 1 where advection is really dominating. When in regime 1, where we have advection dominating, we can solve that advection diffusion reaction equation for concentration in B. And more particular, we can also come up with the non-dimensional number for regime 1, which is the ratio of exposure to reaction timescale, and it involves this. So we have the exposure timescale and the reaction timescale, and again we're using this non-dimensional number. Regime 2 is where it's diffusion. There's much fewer examples of this in the real world where advection is neglected. But the ones I could come up with where diffusion is more likely is a wetland which is at steady state with the groundwater. There's very little groundwater head, and so the transport across the exchange between the groundwater and the wetland could be controlled by diffusion. A very dense canopy, which is essentially choking the flow. Maybe in a mangrove system in the coastal environment where you have very stagnant waters, and diffusion may be controlling the movement of transport across small time scales and space scales, and in porous media flow under very low hydraulic gradients. All of these we could describe as a diffusion-dominated systems. Diffusion-dominated systems we don't like working in because the math suddenly becomes much more complicated. But the thing I'm coming back to is this non-dimensional number, where we have again an exposure timescale, this time related to diffusion. We have the reaction timescale, and we have the non-dimensional number. So we need to know which regime we're in to define our exposure timescales. Just a really brief overview here of this is a mathematical modelling of what happens when you have just advection and transport. So this is a signal of a concentration signal. If you just have advection, that pulse will be moved downstream with no smoothing out of that concentration pulse. This is diffusion with time, so you don't have movement downstream, but you have a smoothing out of the pulse. The overall concentration or overall mass remains the same. It's just been smoothed out. This is if you have a reaction as well as these transport terms. It's what the concentration pulse will look like. The case study I wanted to talk through is of how we use these non-dimensional numbers is that advective recharge of acidic oxygenated water from a wetland to the anoxic groundwater, which in this case is very rich in iron 2. So what we're interested in doing is estimating the depth of the oxygenated zone in the sediments, because that has a profound impact on the microbial community and the biogeochemistry. So what we can do is describe the change in iron concentration or in oxygen concentration. We can solve this equation to get an estimate of our final or a specified concentration. What we were interested in for this particular case study was what is the distance from the edge of the wetland where the oxygen is maintained to about 90% of what it was in the surface waters. And what we can do is that, so there's only a reduction of 10%, so 90% of the surface waters. So using the non-dimensional number, we can come up with an equation for the length scale or the distance from the edge of the lake that is required to decrease the oxygen to 90%. And because we're dealing with an acidic system, we were interested in the difference between whether the system was acidic or not. So at pH neutral conditions, that distance of 10% reduction in oxygen would be 6 millimeters. In this case, it's very much dependent on the kinetics of iron oxidation and iron reduction. At pH 7, the kinetics are very slow. The kinetics are very fast, and so the time scale is very short. The length scale is very short. At pH 4, the kinetics are very slow, and so the length scale is very long. And so at pH 4, which is what these systems are, it means that we have a length scale of 5 meters, where the microbial community is still an oxic microbial community. And after that, it's becoming more and more suboxic and anoxic. So this approach, using understanding whether the system is in regime 1 or regime 2, which gives us our exposure timescales, therefore our N, therefore we can estimate a length scale, and therefore it gives us an idea of whether we need to do our measurements over 6 millimeters or over 5 meters. There's another regime which I'm going to call regime 3, which is quite different again. So far we've just dealt with systems which are hydrologically or hydraulically connected. So they're either connected via groundwater surface flows or they're connected by standing waters, rivers. But but many of our systems that we're interested in are disconnected, at least intermittently. So my question was, is there an equivalent framework for intermittently connected systems? And there is. So the type of disconnected systems that I'm talking about is maybe a wetland that is perched and so disconnected from the groundwater. Maybe a lake or a river that is stratified, so the bottom waters become intermittently disconnected. An oxbow lake that is intermittently disconnected from the river, or maybe under very low river flow conditions, then the reefs and the islands become disconnected from the terrestrial environment. Under regime 3, then neither the advection nor the diffusion becomes relevant anymore. There is no transport. These systems are pure reaction. There may be diffusion within the systems, but there is no transport across systems. We can still describe our concentration of B, and we can still describe a non-dimensional number for regime 3, where we have an exposure timescale, but we're changing the language here again, and instead of exposure, we can actually talk about an isolation timescale. And this starts to feed in quite nicely with some of the concepts from ecology around isolation and connectedness. So the isolation timescale is actually the inverse of the disturbance frequency, which again plugs us into a lot of ecological theory around the effects of disturbance on systems. I now want to move on to some of the ecological consequences. So again, moving more into some of the traditional classic ecological theory, I've taken a figure from Houston et al., Houston 1994, and I've translated the language. So the concepts are identical, but the language was very, very different. So what I've done here is translated it to keep it consistent with the language that I'm using. And Houston proposed that, so here this figure is exposure timescale on the vertical axis and processing timescale on the horizontal axis. So these are our two timescales that I've been going through in this talk. And Houston proposed that when these two timescales are of the same order of magnitude, which means the NE, the non-dimensional number, is of order 1, then that is when you have maximum biodiversity. When you have a very high time scale, so the systems are slow, but a very long exposure time scale, then you get a lower diversity because the populations fail to recover after disturbance. If you have a very long time scale and a very short processing time scale, then the diversity is reduced by composition. So the interesting part becomes, well, if we have a non-dimensional number that we can access through estimating exposure timescale and reaction timescale, then can we predict when maximum biodiversity will occur? Okay, one of the points remains that systems very rarely remain in one regime or another. So we have defined in this talk 3 regimes: an advection-dominated regime, a diffusion-dominated regime, and a disconnected regime. Many systems fluctuate between one regime and the other. So here we have the 3 regimes, and here we have when the non-dimensional number is much greater than 1, or much less than 1, or is about 1. And this is the regime that Houston is proposing that we have maximum biodiversity. So just looking at the 2 extremes, though, the type of behaviour we would expect if we had a non-dimensional number NE much greater than 1, that means the exposure timescale is much greater than the reaction timescale. Then under this scenario, the reactants must be considered non-conservative. So non-conservative is not an absolute, it is only defined relative to the exposure timescale. So under this scenario, reactants must be considered non-conservative, and the connectivity, whether it's hydrological or hydraulic, must be defined biogeochemically. So the biogeochemistry or the reaction becomes really important. If the systems are disconnected, then you'd expect an ecosystem hotspot. And so the isolation becomes really important from an ecological perspective. Over this extreme, there's not sufficient time, exposure time, for reaction to occur. The reactants should be considered conservative. And so the connectivity, material, fate, and transport is really defined by the transport, by the hydraulically or hydrodynamically. Interestingly, in this regime, you would expect this regime or this scenario to be very sensitive to changes in the hydrology, which could be caused by climate change or by urbanization, for example. And so here you would not expect a hotspot to be important, and maybe the isolation is not so important here. When you have the middle context, you're expecting a system which is highly dynamic. It can shift from reaction-dominated to hydrologically dominated. So the balance is very sensitive to the conditions, and you need to characterize both the hydrology or hydrodynamics and the biogeochemistry. So what happens when systems shift from one to the other? If a system is, I'm just going to give 3 examples of this. If a system is moving from regime 3, where you have a hotspot, a disconnected hotspot, and it's moving to regime 1, where you have strong advection, but there's still, the advective timescale is quite long, so it gives the system a lot of time to react, you will have effective but non-conservative dispersal of material. If you have a system moving from disconnection here to advection here, then you have a system that is disconnected, but there's not enough time for the hotspot to occur. And now it's being shifted to an advection regime, but again, the material, whatever it is you're interested, is behaving conservatively, even though it's being transported down. One of the most interesting shifts would be a regime that is disconnected here, but is still disconnected for long enough time for the hotspot to really form. And then it's shifting to an advective regime where the advective regime, it's moving things fast, and so the material is still, it's more or less being conserved. It's acting conservatively. And so here you get a very effective dispersal mechanism where the material is being conserved. And so in this case, the isolation or the disconnection of the system becomes very important from an ecological perspective. So the use of this framework, just summarizing again, it's a classification regime. First thing is to determine whether the system that you're working in is dominated by diffusion, advection, or disconnection. And that allows you to determine your timescales, your exposure timescales, because depending on these regimes, you'll get a different parameterization or different description, or different equation for the exposure timescales. You then can identify the reactions of interest, whether they are biological reactions or chemical reactions, or even particles, inorganic particles that are settling. All of these processes have a reaction timescale, so you need to be very clear on what it is you're interested in. With both of these, we can estimate the magnitude of the non-dimensional number, and that allows us to classify your environment, your system, to determine whether the exposure is more important in your system or the reaction. And that allows you to focus your research effort. Do you spend millions of dollars on your hydrodynamic model, or do you spend millions of dollars doing some biogeochemical sampling or biological sampling? So the magnitude of NE allows you to focus your research efforts, and then finally, by identifying these different space scales, depending on the magnitude of NE, you can actually guide your monitoring effort. Is it over 1 metre? Is it over 10 metres? Is it over a kilometre? Okay, so finally, I'd like to thank a large number of people and funding agencies for this work. There's been, over the last 15 years or so, there's been a number of people that have been very useful for these discussions. It's been great to have collaborators across the world, and the funding has come from a number of different areas. Thank you, and just a plug, there's PhD scholarships available in Australia in this area. Thank you.
thank you very much for an excellent talk. We have time for a few questions. Is the microphone? Excuse me. Is the microphone over there? Microphone over there. So please come forward if you have a question.
This one there.
Oh, it's a question over there.
Okay. I just missed one point. You said advection diffusion timescale in fluid mechanics, we call it the Peckley number, right? Mm-hmm. So what happens if that number is order 1? That means advection and diffusion are playing a role.
Essentially the maths just becomes much more complicated. So there is a reference to a paper, and we actually deal with when the Peckley number is of order 1. And a lot of the context that we're currently working in, the Peckley number is of order 1.
So would that fall in a different regime?
No, we called it a boundary between the regimes. So there's a boundary between the regimes, and then you can still do the maths to come up with the exposure timescales. And then you can continue on. So understanding where your Peckley... So I didn't bring in the Peckley number in this talk, but essentially you're first of all determining the Peckley number to know whether you're advection, diffusion, or in the boundary between the two, and then you can extract your timescales, your exposure timescales, then you get your reaction timescales, and then you can get this non-dimensional, the ratio of the two.
Hi, thanks. It was a great talk. Appreciate it. So what about if you're in a system where you have oscillating flows, like in groundwater systems where you might have seawater advection, groundwater flow, and then you have spatial variability in the hydrologic head? Do you switch between regimes?
I deal with these systems a lot, and this has been a question that keeps coming back. When I think you're oscillating between regimes, whether one regime is more important than the other, or whether it's the oscillation that's most important. Our thoughts at the moment are that you need to be very careful about what your reaction is that you're actually interested in. If the reaction timescale covers the oscillation period, or whether it's really in the one regime or the other, so that determines whether you are fluctuating across regimes or you can really focus on one. And generally what we've been doing is trying a number of those different scenarios and seeing what difference it makes. And it's providing real insight for us into how we measure the ecological side of things or the biological side of things under different conditions, because we're starting to get a feel for the different regimes and whether it's the oscillation or not.
Right. I guess what I was thinking of is, carbon flux from sediments, and if you've got periods of time where it's anoxic, then the water flowing out is going to you conserve carbon, whereas you have that.
And I think I think it's the oscillation. I think that is most important, which is why we started moving into the disconnection and that isolation timescale and the disturbance timescale, because for me, we're starting to think that it's actually that oscillation that becomes most important. So how do you set up the framework to cover that oscillation? And that's what's leading us into the disturbance, essentially taking the disturbance theory concept and bringing it into the biogeochemistry. Yeah.
Time for a short question. Okay.
Thank you.
Thanks, Carolyn, again, for the excellent talk.